Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Lalo and I'll be walking you through the chemistry course. In this particular lesson, we're looking at the rate of reactions, and we'll look at another three subtopics. That's the rate of chemical reactions, we'll look at collision theory, and we'll also consider the factors affecting the rate of chemical reactions. Alright, let's begin. So when we talk about rate of chemical reactions, what comes to mind? In the previous lesson, we talked about reactions, chemical reactions, and we talked about what it involves. It involves amount of heat, a certain degree of heat. And we also know that this heat actually have influence on the reaction, whether it is positive, whether it will occur or it will not occur. So when we talk about rates, when we hear the name of the word rate, it means the speed at which something happens. So when we talk about rate of chemical reaction, it's simply talking about the rate at which, or the speed at which the reaction happens. The rate of chemical reactions can be estimated or calculated by, we say rate should be equal to the amount of products produced, amount, or let me use the word mass now, mass of products divided by time taken. So as each of the products is being produced, how much of product is being produced within a certain duration of time. That is simply what we're looking at when we talk about the rate of chemical reactions. How much of product is being produced at a certain rate of time. Now, the interesting thing about chemical reactions is this: it depends on two different things. You can measure it based on the rate at which the product is being produced, or you can measure it based on the rate at which the reactant is disappearing, or the reactant is being used up. So when you consider a particular equation such as HCl plus this. Now, well, you know the rates, you know how much of HCl is in your system, you know how much of your sodium hydroxide also you have in your system. So when you want to calculate how much of the rate at which the reaction is occurring, you can either take note of this, or you take note of the products. You can either take note of these, or you take note of the products, which are these. Of course, as this one is being changed, it is changed to this. So how much of this is disappearing, or how much of this is being created? So that's how to measure, take note of the rate of change, rate of reaction. Also, how does the rate of reaction vary? How does the rate of reaction vary? The rate of reaction vary based on several different properties. Several properties have influence on the rate of chemical reaction. Alright, we've talked about rate of chemical reactions. In a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson. Please do well by answering them, and we'll see in a few. So we talked about the rate of chemical reaction. Let's look at the collision theory. The collision theory is a theory that proposes that for any chemical reaction to occur, there must be a certain degree of collision. There must be enough collision that it would initiate an energy which is greater than a certain degree of energy, certain amount of energy. And that amount of energy which you are talking about is the amount of energy required for that reaction to occur. So there must be an energy within the system, either equal or greater than that energy required. That energy required is described as the activation energy for that chemical reaction to occur. So, in a particular system, this shows the energy, and this is the time. Now, in exothermic reactions, we have something like this and this. Yes, our reactants are here, and our products are here. Now, between them, we have what we identify as our activation energy. The activation energy is the yield that needs to be overcome. Of course, we know that our properties, our matter, every compound is made up of tiny particles which are in constant motion. So this constant motion in which these substances are in. When you even pour one into the other, it's actually an increase in the rate at which they move. So it can actually lead to them being able to develop enough energy to overcome this barrier. Now, it depends on what kind of substances we're talking about. If there are substances that easily react with each other, they will easily overcome this barrier and the products would be formed. Of course, we also know, and this is for exothermic reaction, and our change in H is here, and it will be negative because the H here is higher, as in the H that enters into the system, the output is lower than the input. So our H will be negative. But in endothermic reactions, we have something like this. Our reactants are here and our products are here. It's still the same. And now the activation energy is the whole of this height, from up there to down here. That's our activation energy. Our H, this is our starting and this is our ending. Let me write it clearly. H1. So this is our starting, this is our ending H. So our change in H will be here. That's change in entropy. And of course, since 2 is bigger than 1, it would be positive. This one, 2 is less than 1, it will be negative. So basically, this is what the collision theory proposes, that a certain amount of energy is required for every reaction to occur. And that energy is the amount of energy required. The amount of energy required is what is known as the activation energy. If you can get up to that energy, fine. If you can get more than that energy, good. But you must attain at least that particular energy for the chemical reaction to occur. Alright, let's look at the factors affecting the rate of chemical reactions. The factors affecting the rate of chemical reactions, like we discussed from the collision theory, we know that these substances need to mix together. And of course, from what we have been discussing so far, I told you about sodium reacting violently with water, while magnesium does not react with water. It requires you to have steam to react. So one of the very first things I'll mention when it comes to the rate of change of rate of chemical reaction is the nature of the substance. Nature of the substance. So substances are highly reactive, while others aren't so highly reactive. Substances like group 1 elements, group 7 elements, they are very, very, very reactive. Substances like group 0 elements, they do not react at all. So you cannot force helium into a chemical reaction. You cannot force it to perform any role because it doesn't see any reason why it should perform any reaction. But if it is subjected to enough heat, probably it will respond and to lose an electron or gain an electron for the sake of being a part of a chemical reaction. Of course, what all elements are looking for is stability. And you find out that group 0 elements have attained that particular stability. So they are not looking for any electrons. And we have the group 1 elements, they are very, very close to attaining stability, but they just got one extra baggage. They would gladly lose that extra baggage to anyone who wants it. And similar to group 1 elements, we have group 7 elements who are so close to attaining it, they just need one extra electron. So they will gladly accept an extra electron. Even if you have 10, they will just take that one that they need and keep to themselves. Elements like carbon find it difficult to make up their mind because they have 4 electrons, they cannot afford to lose all 4. They cannot afford to collect. It's difficult to get someone to give you 4. So they have they are a little more confused. Now, when you consider elements like oxygen, just 2 electrons. It can be, it is achievable, but obviously if hydrogen should appear in a place and we have chlorine and oxygen, hydrogen will gladly attach itself to chlorine. Why? Because it is just needing a single electron. So the nature of the substance goes a very long way to determining the rate at which the reaction will occur. Another thing to take note of is the concentration. The concentration of the substances. When we talk about concentration of the substances, if you have a bottle of Coke, you taste it, you put it in your mouth, and you take a dilute Coke, and put it in your mouth. Of course, the tastes won't be the same. The same way it works. When you have something in the concentrated form, they tend to react more. When you put Coke, the undiluted one, in your mouth, the undiluted one in your mouth, you feel the taste more effectively. So when you're thinking about the concentration, it talks about how much of a substance is inside a thing. We talked about concentration earlier in this lesson, in one of our previous lessons. When you take a bottle of Coca-Cola and you open it, you put it in your mouth, the taste is different from when you dilute it with water before you take it in your mouth. So you see the rate at which the reaction occurs is also different. That's the same way it works when you talk about the concentration. When you take concentrated H2SO4 and you react it with certain metals such as potassium, you see a very violent reaction. But when you react it with that same potassium with dilute H2SO4, that's tetrahydrosulfate 6 acid, you'll see a reaction that is reasonably normal. So oftentimes we react strong acids with dilute bases, or dilute acids with normal bases, sometimes even with ordinary metals, especially when we're working with acids. We dilute our acids when we want to react them with high electronegative metals. Also, apart from the concentration of the substances, we also consider the surface area. Surface area of the reactants. You see, when you have a lump of potassium and you drop it in water, it will react, but it will not react as fast as when you have granulated potassium poured into water. Even though they may be the same mass, the one with a larger surface area, which is the ground one, would actually react faster. Why? Because the rate of collisions is increased. The rate of collision is increased because of the large surface area. Then there is more bombardment, there is more collision between the molecules of the substances, so it increases the rate of the chemical reaction. When there is a wider surface area, there is a larger rate of reaction. Also, we have the effect of temperature. The effect of temperature. Temperature does not have effect on all chemical reactions, but most chemical reactions are affected by temperature. Yes, most chemical reactions are affected by temperature. Earlier in this, in one of our earlier topics, when we're talking about groups of periodic table with family of elements, we mentioned that group 2 elements react with water, and we specifically talked about calcium. We said calcium reacts with cold water very slowly, but when you warm up the water, it reacts at a faster rate. So when you increase the temperature, you are increasing the chances of bombardment of molecules, of atoms within substances. So when you do that, you increase the chances of collision. So you see that everything boils down to collision, the collision of the substances, and then you have a faster reaction. At low temperatures, generally reactions are mostly slower, but at high temperatures, reactions are generally mostly faster. Also, the effect of light. The effect of light. Not all chemical components are affected by light. Some chemical components are kept in brown bottles. Why? Because such as trioxonitrate 5 acid. It is kept in brown bottle. Why are these compounds kept in brown bottles, colored bottles? Simple reason. When white light reflects or transfuses or diffuses through them, it decomposes the structure, it decomposes the constituents. Also, you discover that for photosynthesis to occur, light must be involved. It's not like it is the light that the light is just like is serving as a catalyst. So sometimes light affects the rate of reaction. Light affects the rate at which the reaction occurs. It also might actually hinder the reaction from occurring for those particular chemical components which have relationship with light. That is, those ones that work with photons. That is photo and light energy. And conclusively, we have the effect of catalysts. The effect of catalysts. A catalyst is any substance which is used in a chemical reaction but does not actually take part in the chemical reaction. It makes the reaction happen either faster or slower. It can either fasten or hasten the reaction or slow down the chemical reaction depending on what you want the catalyst to do. So we see these are the 6 pointers to influencing the rates of chemical reactions. All right, in this particular lesson we looked at the rate of chemical reactions. We talked about the rate of chemical reactions, how they are calculated. We talked about you using either you consider the rate of diminishment of the rate at which the reactant is being diminished, or the rate at which the product is being created. We also talked about the collision theory that suggests that there is a barrier that needs to be overcome for every reaction to occur, and this barrier is the activation energy. It has to be overcome for any reaction to occur. We also talked about the factors affecting the rate of chemical reactions. These are the nature of the material, the concentration of the material, the surface area, the light, catalyst, and as well the temperature, the role of temperature in influencing the rate of change, rate of chemical reactions. Alright, in this lesson we have talked about a lot of things, and as such we ought to ask ourselves a few questions. So in a few seconds some questions will be displayed on your screen for you to answer. Please answer them, and if there is any part of the question that confuses you, you can go over the video one more time for clarification. Thank you.